Nomine Patris et Filii et Spiritus Sancti. Amen. Veni Sancti Spiritus, Revelatorum corde fidelium et tui amoris in eis in accende. Miti Spiritum tuum et creabuntur, et renovabis faciem terrae. Oremus Deus, qui corde fidelium Sancti Spiritus illustratione docuisti, da nobis in eodem Spiritu rectus sapere et Deus semper consolatione cadere, per Christum Dominum nostrum. Ave Maria, gratia plena Dominus tecum, benedicta tu in mulieribus, et benedictus fructus ventris tui, Iesus. Sancta Maria, Mater Dei, ora pro nobis peccatoribus, nunc et in hora mortis nostrae. Amen. Sit sapientiae, ora pro nobis. Sancte Roberte, ora pro nobis. In nomine Patris et Filii et Spiritus Sancti. Amen. All right, today's lecture will be a little bit of review. We've already used and discussed the Pythagorean Theorem in class earlier in the year, but we'll go over it again because it's extremely important, and we're going to see a couple of new aspects of it. And also we're going to prove it. We're going to use what we know about the geometric mean to actually prove that the Pythagorean Theorem is true, and that it does work in the case of every right triangle. So the Pythagorean Theorem, again, it's named after Pythagoras, who was a Greek mathematician, scientist, and he came up with this theorem based on the idea that if you made a square from the side lengths of a right triangle on each side, that the two smaller squares of the two legs would add up together to be exactly equal to the area. Their areas would add to be equal to the area of the square on the hypotenuse. Okay, and again, the hypotenuse, just some quick terminology reminders, the hypotenuse is the side of the right triangle across from the right angle, okay, or opposite the right angle. And the other two sides are called legs, and these are what the variables a and b stand for in the Pythagorean theorem. They are the lengths of those legs of the right triangle, and c is always going to stand for the hypotenuse's length. So we can actually prove that this equation is true for right triangles if we use the idea of the geometric mean, which we covered yesterday. The second corollary for the geometric mean said that that the leg length is the geometric mean between the length of the hypotenuse and this segment of the hypotenuse that comes from this altitude dividing the hypotenuse into two sections. And so we can write, for example, that this proportion that C to A is equal to A to E. Okay, and A is the geometric mean here, okay, in the way that this proportion is set up. And likewise with B, the other side length, we can also do a similar thing. We could say that C over B is equal to B over D. And then we can do some algebra with these two statements to come up with the Pythagorean theorem, in fact. So if I cross multiply these, you get a squared equals c times e, and b squared equals c times d. And if I then take these two statements and I add them together, so if I do a squared plus b squared, then I can say this: a squared plus b squared is equal to, well, a squared is CE and b squared is CD. So it's the same thing as saying CE plus CD. And then we just pull a little factoring trick here. C goes into both of these, so we can factor it out and say that this is C times E plus D. And E plus D is just, well, it's the same thing as C. It's just C divided into two separate segments. So I can actually substitute C for that here. So it's C times C, which is just C squared. And so we end with A squared plus B squared equals C squared. And since this is this right triangle is not any specific right triangle, it's representative of all right triangles. This is true for all right triangles. The square of the lengths of the legs, the sum of those squares will be equal to the square of the hypotenuse. So we have proven the Pythagorean theorem. Okay, there are, as I said before, there are other ways to prove it. but this is the one using proportions and using the idea of the geometric mean. So a quick refresher on how we might actually use this in an actual problem. So I have this prism here, this triangular prism, and we can see that on this face there's a length of 9 and 12, and then we have an unknown hypotenuse, so something here, let's just call it y. And then the front face side of this prism, it has a diagonal passing through it, which is the length of 25. Well, that diagonal is the hypotenuse of this triangle. And if I knew y or x, I could use the Pythagorean theorem to find this other value, but I don't. So I need at least 2 of the sides of the triangle to use the Pythagorean theorem to find the third missing one. But if I do 2 sets of Pythagorean theorem operation here, so I can use the Pythagorean theorem to find y on this smaller triangle, and then I will know what y is, and I can use that in conjunction with this length of 25 to find what x is. So let's go ahead and work through this. So these are my legs on the smaller triangle, 9 and 12. So that means 9 squared plus 12 squared is going to be equal to that hypotenuse, which we're calling y squared. 9 squared is 81. 12 squared is 144. Those add to, 215? No, 225. 225 is y squared, and then if I take the square root to solve for y is going to be, actually square root of 225 is 15. So we know this side length is 15, and now we can use that with the 25 to find x. So be careful now though, sometimes people will make the mistake, they'll think, oh, well, whatever the variable is, that's what's going to go here for the hypotenuse. No, the variable goes wherever is appropriate depending on what part of the triangle it's representing. So x here is one of the legs, so we have to actually add it here, 15 squared plus x squared, and the hypotenuse is 25. So be careful about putting things in the right place here when you're substituting them into the formula. 25 squared is 625. 15 squared we just saw was 225. So if I subtract that, I'm going to end with 400. X squared is 400, and this is a nice, relatively easy square root. In fact, the square root of 400 is just 20. 20 times 20. So we've used the Pythagorean theorem twice here in the same problem to find this unknown. So that's just a little refresher, an example of how to use it. You should already be comfortable with that idea. We did some problems last week of this form, although we weren't actually applying it to geometry. They were just algebra problems represented like this. Okay, something we haven't talked about yet with the Pythagorean theorem is that the converse of the Pythagorean theorem is also true. So not only in a right triangle is a squared plus b squared equal to c squared, but if I have any triangle and I find that a squared plus b squared is equal to c squared, then that means that the triangle is a right triangle. So we can actually use this to check what type of triangle something is. If c squared is equal to a squared plus b squared, the triangle is right. If c squared ends up being less than a squared plus b squared, then it's not a right triangle, but that actually means it's an acute triangle, and we'll show you why it's acute in a second. If c squared is greater than a squared plus b squared, then the triangle will end up being an obtuse triangle. And okay, the reason that less than is an acute triangle and greater than is an obtuse triangle is if you think about, okay, the equality is when it's a right triangle. So if a squared and b squared are equal to c squared, then it's right. But if c shrinks, so if c, when I square it, is less than these, that means c will have to have become smaller. So if I shrink c, then what's going to happen in relation to A and B is this angle is going to have to close. This angle is going to have to become smaller. And so if C becomes smaller, and so therefore C squared is less than this, then that means this angle is not a right angle anymore. It means it actually shrunk below 90 degrees. And so the triangle will be acute. If C ends up being greater than A squared plus B squared, then that means C would have to have lengthened from what it was in the situation with the right triangle. And that means that A and B are then going to have to spread further apart, and this angle will become larger than 90 degrees. And so the triangle will be obtuse. So we can use this idea to, if I have just random triangles and I don't know what type of triangles they are, I can plug in my information into the Pythagorean theorem and compare whether there is equality or not, and then dictates what type of triangle it will be. So for example, if I know that I have a triangle with side lengths 11, 11, and 15, I can plug those into the Pythagorean theorem and see what happens. So be careful again here. The longest one of the largest number is going to represent the longest side length. So that has to be what you plug in for C, since C represents the hypotenuse, and the hypotenuse is always the longest side of a right triangle. So make sure that you put the largest number, the largest value in for C, and then the other two, which are smaller, in for A and B. So here in this case, we'll say that A is 11, B is 11, and the hypotenuse or the potential hypotenuse is 15, okay, the longest side of the triangle. So 11 squared plus 11 squared, is that equal to 15 squared? Okay, we don't know. We're going to check and find out. And 11 squared is 121. 15 squared, as we saw before, is 225. So this 121 plus 121, this adds to 242. It's definitely not equal. Okay, so this is not a right triangle. 242 is greater than C here. So that means C is less than A squared plus B squared. And so this triangle is actually, this is an acute triangle. If my side lengths are 0.5, 1.2, and 1.3, well, actually, I'm going to cheat a little bit here. I know that this ratio is actually a right triangle. And there are some common right triangle configurations, like you will see, if you see side lengths of 3, 4, and 5, that is always going to be a right triangle. Another common one, which pops up a lot, is 5, 12, and 13. That will always be a right triangle in those proportions. And this is just a disguised form of the 5, 12, 13 right triangle, because we have just taken these and we've divided them all by 10. So we've moved the decimal point in one place. So we have 0.5, 1.2, and 1.3. But that's basically the same thing as 5, 12, 13, okay, as far as the proportion. They're similar. But anyway, if you didn't know this, you can still plug and chug here. You can still check it out that way. So if I do 0.5 squared plus 1.2 squared, is that equal to 1.3 squared? We don't know. 0.5 squared is 6. Oh boy. Bear with me. Is 0.25. 1.2 squared is 1.44, and 1.3 squared is 1.69. And if I add these, I get 1.69. So this is exactly equal to the C squared here. So this triangle is indeed a right triangle. So the algebra verifies, or the arithmetic, I should say, verifies the thing that I was talking about here earlier, that this will be right. Okay, one final example. If I have 10, 17, and 18 as my side lengths for the triangle, again, 18 is the longest, so that's going to be the potential hypotenuse. Is that equal to 10 squared plus 17 squared? 10 squared is 100. 17 squared is 289. 18 squared is 324. So this is 389 versus 324. So the 324 here is less than 389, excuse me. So again, this triangle will be acute, since the hypotenuse is squared is less than the sum of the legs squared. Okay, so these are some examples of how we can use the Pythagorean theorem in practice, and that should be enough for you to do tonight's assignment. Again, as always, let me know if you have any questions or are confused about anything.